দেখা যাচ্ছে?
This call is now being recorded.
Hello.
Yes, we can see your screen. Okay, so let us start.
Okay.
Welcome everyone to this weekly seminar on quantum information. And today our speaker is Sumit Mukherjee, and this is the second part of what he started talking in the last meeting. So this is about contextual fraction as a measure of contextuality. So we are having this session in an unusual time, but from the next week, I guess, we will go back to our usual time. And so let's start, Shumik. And if anyone has questions, they can unmute themselves and ask the questions. Okay. Thank you.
Yes. Yeah, thank you, Somda. Okay, so to start with, I will just recall the notations that I have used in the last talk. Okay. So I started with three things. These three things, where X is the measurements, M was X is the set of measurements, and M was a subset from the set of measurements that I called context, I mean set of contexts, and O are the outcomes of the measurements. Okay, so when I write C stands for context, and C is in M. Okay, so M is the all set of all context. Okay, whenever I write OC, that means it is the set of outcomes of context C. And okay, so this is what. And second thing, what I introduced is the empirical model. That is the main thing in our discussion last day. So what is the empirical model? It's a table of data, and for understanding, I just introduced a table of data in the CHSH kind of scenario, where say this has the observables of Elisa and Bob, A1, B1, A1, B2, A2, B1, A2, B2, 0, 0, 0, 1, 1, 0, 1, 1, 1. So this is a particular table of data. You can fill it with your choice. Maybe let's say I am filling it like this. So you can recognize it. Maybe it is a particular empirical model which is used for the peer box kind of correlation. You can have many other empirical models. So these are just the probability that you obtained in your experiment, and you record the data in such a table. So this is in a two-party, two-input scenario, two input and two output scenario. Okay, so I referred this empirical model and represented it by something, a small e. So this is my empirical model E. Okay, so these are all the notations. So the last thing where I stopped that day was that any empirical model can be written as a convex combination of an empirical model that is non-contextual and another empirical model that is some no signaling model. Okay, and later I said that it is proved that any empirical model can be represented as some and okay, so I said this. So any empirical model will be represented by such a combination where this model is non-contextual and this model is strongly contextual. And this is a coefficient which is non-contextual fraction, and this coefficient is the contextual fraction. So our main discussion will be centered around this contextual fraction or non-contextual fraction, because as it is a convex combination, so contextual fraction equals to 1 minus non-contextual fraction. Okay, so I will today discuss how to calculate this contextual fraction. So to introduce this, just again remember our scenario is fixed. This is my scenario. Now I will introduce two numbers. Say one number is n, that is the cardinality of this set. This set is what? Ox is the set of all outcome of all measurements, because x is my measurements, all set of all measurements. So Ox is the set of all outcomes of all measurements. So in the CHSH kind of scenario, how many will be this cardinality? In this kind of scenario, two party, two input and two output scenario. So this is essentially 16. Okay, and another number I will introduce is this one. This is C, and C will be in M. Okay. So that means what? The sum of cardinality of all the outcomes of all the contexts. So these are my two numbers. So previous day I discussed that, okay, if I have given a model E, can I represent it in a non-contextual way? That means, can I assign some global probability distribution out of which I can recover all the probability distributions of individual contexts? So I will proceed in the same way. I define a matrix M.
Sumit.
Yeah.
So in your this two input, two output cases, what will be this M? Because you said N is 16, and what will be this M?
Okay, so Ox means all the outcomes of all the measurement, right? So that means your measurements was A1, A2, B1, B2, right? And each measurement has two outcomes, 0 or 1. That means what are my X? 0, 0, 0, 0, 0, 0, 0, 1, and so on, right? 1, 1, 1, 1. Right? So you have 16. So this cardinality of this set is 16. That means n equals to 16 in this case.
Yes.
Okay.
And what is M? Small m.
Okay, so small m is sum of the cardinalities of individual context and sum over all the context. That means what is your context in this scenario? Your context is A1, B1, because A1, B1 can be measured jointly, right? Again, your context is A1, B2. Your context is A2, B1. And your context is A2, B2. Then OC means outcomes of the set C. Let's say this is my C set. This set is C. So then OX is what? 0, 0, 0, 1, 1, 0, 1, 1, right?
Yes.
And then when you sum over for all this C, this is also a C, this is also a C, you will get again 16, right? But this is a symmetric scenario, that's why M and N both are 16. But you can have some other scenario where M is different and N is different.
Good. Okay, thank you.
Yes. Okay, so now I will introduce one matrix M whose elements, they depend on three things: context, the outcomes of a context, and some G. G I introduced in the last talk, right? G is the global assignments of outcome, global deterministic assignments of outcomes. Okay, so how this matrix look like? this will be a m by n matrix. So why I am introducing this kind of a matrix, that will be clear in a little bit. And this m, which is a function of c, s and g, this will take value 1 whenever g given c coincide with s. G is my global assignments, and from the global assignment, if I specify the context, if it return back to the outcome of that context, then value will be 1 unless the value will be 0 in this matrix. Okay. So now I will introduce another thing, which is a vector, and this vector is some d, say. So this vector lies in this dimension, n dimension. Why I am introducing it? Let's say I multiply this vector and get some other vector. This is my matrix M. I multiply this. So if I want to multiply, so it should be n cross 1 matrix, and this should be m cross 1, right? So D is the probabilities of global assignments of outcomes. That means here I will have some probability over G. Okay. And this vector I will call it VE, a vector for the empirical model E. That means what is happening? You are discovering one matrix M, which upon multiplying with such vectors which contains probabilities over G, it is returning back to the statistics I get from the table. So for your understanding, what will be this vector VE? So I have written this table here. So VE will be just a flattened version of this table. Let's say this vector has 16 elements. So 4 will be from the first row of this table. 4 will be the, so from this table, this 4 element will be first, then this 4 element, and this 4 element, and this 4 element. That means at the end of the day, what I am doing, I am discovering a matrix, and which when multiplied with this vector, that vector contains the global probabilities, is giving me back the empirical model itself, right? So if I can do that, then that model is non-contextual, what I discussed last day. It is another way of saying.
Sumit,
Yeah.
but I'm asking, your this D, which belongs to Rn, this is these whole things, this n cross 1, okay, but it is a some part of your column is sum to ones. So there is a total. So is there any restrict? Obviously, there should be some restriction on this n cross 1. This total sum would be cannot be more than 4. It has to be equal to 4.
Okay. So that, yes, that should be there. So what is that thing? So if I multiply this D, this should return 1, because see, these are all the probabilities, no?
Not only that, these are this. If you take this column sum, it would be equal to 4, right?
Column sum.
I mean, in this n cross 1, if you take the sum of your elements, it would be 4, right?
It will no. It will not be 4, because G is what? G contains is 0, 0. I mean 0, 0, 0, 0, 1, 0, 0, and those things, right? So the probability of getting one of them will be 1, right?
Yes.
So that means if you sum all these elements, it will give you 1. That is what I am doing here. So D into some matrix which has all the element 1, it will give back 1, because this is a valid probability. I mean, I made this column matrix by a probability, by the probabilities.
I got your point. So that means in your earlier in your earlier step where you have written the PR box, actually there can you go to that? Can you
Yes,
go
yes,
to that?
yes.
So actually it should be instead of this half, because choosing the probability of A1 B1 it itself is 1/4. Choosing the probability of A1 B1. So
A1 B1.
A1
This
B1,
one.
because
This one.
if I take A1 B1, then if I take A1 B1, then coming then outcome probability of 0 0 is half. But
Yes.
actually what is, so your this n matrix is, so your this n cross 1 matrix is constructed with these elements only.
No, n cross 1 matrix is constructed with the global. See, there is only 0 0, means two measurement of one context, right? But see, the n this element, this d is constructed with such probabilities over g, no? But g is what? The four things. These four things. What you are telling for the PR box, I want to reproduce these statistics and these statistics and these statistics. That contains in this table. In this table. The empirical model is this one, VE vector. And this is the hidden variable model, this one. So how can I maybe P of G some. Okay. Okay, so one matrix that contains 0 1 element only. I am arbitrarily writing 0 1. That when multiplied with these hidden variable probabilities, I mean a matrix constructed with the probabilities over hidden variables, that is returning back my empirical statistics that I observed in real experiment. If I can do that, then this empirical model that I am talking about is non-contextual. Right?
I'm just curious about this thing. This PG, okay? So is this PG? Can you write it for me? So
yes.
So this PG is equal to, you write PG is equal to
is equals to
probability of in bracket A1 is equal to A, B1 is equal to B,
A1 equals to A.
A1 is equal to 0.
Okay. A1
equal to 0. B1 is equal to 0.
0.
And their corresponding outputs for example, let's output of A1 is equal to 0. So this A1 0 means I'm choosing this A1 measurement, 0 measurement, B1 is 0 measurement, and their outcome 0 0 measurements.
Okay, so then I should not write only A1 is you are choosing 0, right? A1 B1 is sufficient to represent that, no? A1 B1.
Yes.
When you are choosing first, and for B1 also first, for B also first.
Yeah. Now in your previous matrix, you go to your previous matrix in the PR box.
Yes, this one.
This probability, what is written there inside, it is actually these halves are, or these elements are P over 0 0 output given some AB, right?
Yes, right.
And actually your PG is not that. Your PG is actually
PG is not that. PG is not that.
Your PG is actually probability of AB as well as their outputs.
Yes, PG. No, not AB. PG is actually, say let me write it explicitly what PG is. PG is this one, say one. I am writing one of the PG. A1 equals to 0. I measured A1, get 0. A2 equals to 0. B1 equals to 0. And B2 equals to 1. Let's say this is 1. This is one PG.
I see.
So from this, I am trying to construct A1 equals to 0, B1 equals to 0. Okay. So see, so this is the smaller one. This is the larger one. This is the smaller one. So smaller one is what you are talking about here. So here only two measurement this probabilities are reflecting probabilities of outcomes of two measurements which resides in one context. No,
Good.
but that
Okay.
is coming
Thank you.
from the great probability distribution. Can I reproduce it? If I can, then okay, my model is non-contextual.
Good.
Now it is understandable.
Yeah, it is clear. Now clear.
Okay. So this is now my goal, that I will write a matrix into another column matrix and will reproduce this V. If I can do that, then my model is non-contextual, this E model. But you know that scenarios, even if I want to write for this model, this peer box empirical model, I cannot write this. No, because there is some contextuality or non-locality, you may say. But okay, so I cannot do for some model. So those model, I will call those models are contextual. Yes.
Sumit, just sorry to interrupt you once again. So actually, it is about if there exists some joint probability distributions. From
Yes.
there, if you can get some probability distributions like a. So it is reminding me the Fine's result, right?
Right. Exactly similar kind of things are going on. I mean,
Okay.
if a great probability distribution from which you want to infer the probability distribution of individual context. If you can consistently do that, then you have this hidden variable model.
Good. Okay.
So it is non-contextual, but most of the time, maybe for quantum theory or maybe for some contextual theory, we will fail. So we cannot have such a matrix M and such a D, such that, let's say for some EQ, for quantum theory, let's say I cannot reproduce this. So what can I do? I said in the previous discussion that can I discover at least a sub-probability distribution which can explain a fraction of statistics? If I can do that, how to do that? So let's say instead of D, I have another column matrix B that also reside in the same Rn, and now my expectation is I multiply with sorry, this is B. Now I multiply it with B and I reproduce statistics EQ. Okay, this is less than B or maybe less than equal to B. Can I do this? That means some fraction of events are explained by this B, but other fraction of event is not explainable by this B. So what is this B? So this B, if I take this is not 1, right? If it is 1, then I have my D. So this is only a column matrix I constructed from a sub-probability distribution. So now I am defining the problem. So this has now, see, this has become a linear programming problem. No, so your target is to find a B in Rn, and where you maximize this identity dot B subjected to M dot B less than equals to your VE, and this another constant is this B greater than 0. So now finding the contextual fraction now became a linear programming problem where my non-contextual fraction of E is actually identity into some B dash, where this B dash is the optimal solution of this linear programming problem. No? So this is how I find my non-contextual fraction. And if I can find the non-contextual fraction, then I can just find my contextual fraction. Or maybe if you see that this linear programming problem is difficult to you, you can use the dual problem of it and then solve it, and then you can find directly the solution. So this is how we calculate the contextual fraction. So now I will come to some important results in this direction. So till this point, is it clear?
Yeah, this is clear. This is perfect. So just one thing I wanted to ask you. So that means what we are saying here. So you see, you actually looking into a particular type of statistics, some finite number of statistics, and trying to see in that finite statistics or finite, what should I call it? Finite data set. With that finite statistics, whether how much non-contextuality is there, or how much, what is the maximum value of non-contextuality is there, right?
Yes.
So, for example, the same things one might ask that, okay, I have given you some non-local correlations, and can you tell me that? So, suppose if someone give me some PR box, and then then it is impossible. There is a no, because this is already extreme points, right?
Extreme, yes.
The point is, if something is in the middle, then the problem is, okay, which one is the closest local point which help it to express with the PR boxes, and find that one.
Right.
This is the main thing.
The extreme points of PR boxes and maybe some local.
So maybe some local.
Writing convexly, can I represent some data?
And then we can we can say, okay, this is the non-locality. This is the maximum non-locality.
Yes.
In that correlation, the same thing is happening in your in the contextual case also. You are actually looking into the okay, for those given finite number of statistics, for those given measurements, which one is the closest non-contextual data set I have, which helping me to. So this is the main problem, right?
Yes, this is the main problem. Yes.
Okay.
I mean, how much you can do with like how much non-contextually you can explain some given data table.
Yes. Okay.
So more this be, more your contextual, like more this quantity, more your non-contextual fraction. That means more classicality is there in this model.
Okay. Thank you.
Okay.
Good.
Okay. Okay. So I will just connect it to some CHSH violation kind of things now. Some results. These are some very important results in this direction. Okay. So now, in this scenario, we know what an inequality is. I mean, some local inequality or non-contextual inequality is. So in this scenario, how to define an inequality? So it is characterized by some vectors, let's say A, that is in Rm, because M is what? M is my total number of outcomes of each context, sum over all these things, right? So A is another vector in Rm. Now I can write something like this, no? A dot VE vector. So V is my data, this vector. This vector is V. So V is actually the table. Actually the given table is V. I have written it in a vector form only. VE is actually representing the empirical model itself. So A dot VE, let's say A dot VE less than equals to some beta. So see, this is an inequality. You can write Bell inequality I mean, in this way, no? So basically this VE contains all the probabilities of individual context, like say V, let's say for CHSH kind of thing. I'm just comparing it for better understanding. So what we basically calculate in CHSH, this expectation value, and these expectation values contains this probability of 0, 0, A1, B1, and probability of 0, 1, A1, B1, and so on. These four probabilities. So basically these elements of this VE are these probabilities. These are coming from single context. And when you write the CHSH inequality, it looks like something like A1, sorry, I should write here, A1, B1 plus A1, B2 plus A2, B1 minus A2, B2 less than equals to 2. So basically, see, you are writing the CHSH inequality in this form exactly. No? This A is some number which contains +1 and -1. One vector that contains +1 and -1. Okay. So if this inequality A dot VE, what I am writing, is satisfied by all non-contextual model, then I say this is a non-contextual inequality. Okay. But given some model, let's say I have given you some other model for which this vector is VEQ. Maybe from quantum theory, I have produced some empirical model. By electrons, I have done some experiment and I got some data table. And from that, I produce this VEQ. So that will essentially violate this inequality. If I have chosen my states and measurement in a particular way, then I can violate this kind of inequality. Let's say that violation comes like this: VEQ into A equals to some beta Q. Then my violation is actually what? Beta Q minus beta. This is my violation. And if I normalize it by some normalizing constant, how can I get the normalizing constant? Let's say this. Okay, so the weight of A is, let's say something, this one, A mod A. I am writing it like in this way. So the normalized violation is then what? This mod A minus this beta, and I should actually write it like this: 0, this, because there is no negative violation, no? So I have to write this quantity like this: maximum of 0 or this one. Okay, so I am defining this to be the normalized violation n. Now I'm coming to the result. So this is proved that the normalized violation of a inequality by some empirical model is at most the contextual fraction. That means n is at most the contextual fraction of E. Let's say NE, I am writing NE. NE is the normalized violation of some inequality by this model E. So first result is this. And second result is this, that if this contextual fraction for a model is greater than 0, you can always get an inequality like this. So these are two very powerful results in this direction. Okay, is it understandable at this point?
Yes. But Sumit, I wanted to make I wanted to understand the analogy with the non-locality. So,
Yes,
for example, if I just look into the data set or statistics of 2 input 2 output cases, okay, the first thing is that we already know that there exists a finite number of extreme points, local extreme points, okay.
Yes, yes, yes.
As well as we also know that since there is a finite number of local extreme points, we know their facet inequality.
Yes, yes.
And those facet inequality are the Bell inequality.
Bell inequalities. And some are
So-
non-zero conditions. Yes.
Yes. So now one might say that, okay, so how much non-local a given correlations, a given data set is? Then one of the approaches, how you said that, okay, I do the linear programming and try to see, okay, I would add the corresponding PR as well as the local, and how much local fractions I can increase to reproduce that quantum correlations. And I would say that is my non-local fraction of non-local fractions of that correlations, or maybe non-locality.
Yes.
But then when we come to the questions of inequality, then we would say, since we know the all facet inequality, we try to see among this all facet inequality, which one is giving me the lowest value. So all would be, so some of them would be so
giving
first of
lower violation, or some of them will be giving greater violation.
Greater violations, but all of them would violate anyway, right?
Yes.
-2 to, so if it is local, then it has to be bounded by -2 to +2, but some of them can be very high, -6 also. I don't know.
Yes. So your argument is coming from this first point. So you have maybe many inequalities, and you violate, and you get, let's say, NE1, NE2, NE3 from 3 different inequalities. So
among this, I will take the minimum one.
Among this, you will take the minimum one. Violation.
I'll take the mod of all of them, because in case of a Bell inequality, it could be minus plus, right? So in terms of Bell inequality, so I'll first normalize them, or in this way I'll take a mod or something like that, and then I'll choose which one is the lowest, which one is the which Bell inequality give me the lowest value.
Lowest value, yes.
And then I would say, okay, from that would be my measure of non-locality in that states. Or from that perspective, I could say that would have a connections with the non-local fractions of that correlation.
Fraction, yes. So, but see, one thing from this result is coming from that whatever inequality you use, this normalized violation of that inequality cannot surpass the contextual fraction of it.
Exactly. Here also, that's why I'm saying all the Bell inequality will show me violations. Some of them would be higher, but I will choose the lowest one, because lowest one is that one which is the corresponding facet inequality with that local correlations, which is helping to reproduce that correlations in the maximal way.
Yes.
Okay. So it is a exactly similar kind of thing is happening will happen in the non-locality scenario also, which is known.
Yes. So actually, non-locality scenario is a subset of this contextuality scenario.
Good. Okay. Just another point. So you see, you in the non-locality scenario, we can talk about the extreme points, local extreme points. Also, in non-contextual scenario also, we'll get some finite number of extreme points.
Yes. Non-contextuality scenario, yes. We can get some finite number of extreme points. Yes.
Extreme points. And what will be so later at some point, please discuss these things. What will be this finite number of extreme points, how they will look like.
Okay. So this is my target was to find a quantifier of contextuality. So this is now I say that, okay, this is contextual fraction is a quantifier of contextuality. But if it is good or a bad quantifier, that now I will discuss.
Okay.
So how to discuss that? I mean, then you have to go to the resource theory of contextuality. No, so I'm just reminding you the resource theory, the tools of a resource theory. I mean, what is a resource theory? I mean, that can contain some elements like systems or operations or maybe some phenomena that are useful in some task. So those are called some resource, no? Resource. Okay. So in the resource theory, there are some objects. So first is a free object. Okay. So if I consider resource theory of entanglement, but there are maybe many resource theories for non-locality, coherence, and incompatibility, and so on. But I'll just giving some analogy while discussing. Like for entanglement is the resource, state is the resource objects, and entanglement is the resource. And what is the free object? The tensor product states or the product states. And second is what? Free operations. Free operations are what? Those operations under which this resource do not increase. Right? For entanglement, it is LOCC. For non-locality, it is LOSR and so on. And third tool is a measure. When I'm formulating a resource theory, I have to just represent these things very accurately. And fourth thing is monotone. So monotone is what? Is some function of resource object that do not increase under these free operations. Okay, so in kind of like in entanglement resource theory, it will be this concurrence and entanglement of formation and dist level entanglement, those things. Okay, so now
What is the difference of measure and monotones here?
Yeah, so you can have some measure. You can produce some measure of entanglement. That is maybe a good measure for some scenario, but later you see that this measure is actually always not increasing under free operations. So that measure is not a monotone. That is why I separated measure and monotone.
Okay, some non-monotonous measure you are saying.
Some non-monotonous measure, yes. Okay, so these are the resource theories. So tools of resource theory. So okay, so I will try to establish that this contextual fraction is a monotone and in the resource theory of contextuality. So in the resource theory of contextuality, so the free object is what? Free object is a empirical model. Now see here, it is different than other resource theories. Here my resource object is the data table itself, and the free object is a non-contextual empirical model. Then free operations are what? So I will come to what are the free operations. Essentially, that will transform, like some operation that will transform one empirical model to another empirical model. Those are free operations, but what we should remember that this contextual fraction of E dash should be less than or equal to contextual fraction of E, right? Okay, so some physicists, they start from free operations and then formulate monotones, and some physicists, they start with monotones and then formulate the free operations. So there is a little bit of confliction between physicists around the world. Okay, so and monotone is what? Monotone is contextual fraction itself. Okay. So it is established actually by several papers, including this contextual fraction of as a measure of contextuality, and this is kind of the maybe third or fourth paper in this direction. So it started with some paper written in 2012, and this paper is maybe written in 2018, and later they formulated the resource theory of contextuality in a very formal way. Okay, so what are the free operations? Free operations here are some maybe some map that takes one empirical model to another empirical model, but which is context preserving. That means the definition of context should not change in these two empirical models. So this operation is a free operation in the resource theory of contextuality. Okay, so second free operation is the coarse graining of outcome. I am not going into the details of those things. Second is the outcomes. Third is when you write two empirical model in a tensor product. So what is the meaning of this tensor product? Maybe I have written E tensor product E dash. In the state, we know what tensor product means, but two empirical model written in a tensor product, what does it mean? This means that you can write two empirical model in this way only when those two empirical model can be operated simultaneously without affecting one another, similar to the case of states. So it is just the difference is that here the objects are empirical models. So this is also an operation, taking tensor product of two empirical models. So that is also a free operation. And there are few more free operations. Considering all these free operations, later in resource theory of contextuality, they formulated a giant free operation, which is now, accepted as a free operation. But not all physicists accept that free operation. That is a very large, at least mathematically, that is a very large looking free operations, which they call the giant free operation for contextuality. But under that free operation, it is shown that this contextual fraction is a monotone, and so now it is accepted that contextual fraction is a good measure of contextuality. So okay, so I just wanted to convey this much.
Okay. If anyone else have any questions.
So,
Okay.
Sumit, so who wrote this paper? The last one, which you are talking about.
The giant free operation.
Okay, the giant free operations, and that before that one.
Yeah, that is actually one paper by I forgot the spelling. Maybe Carvonen.
Is it
in PRL?
is it published?
Yes. Right? That is contextuality and non-locality do not admit catalyst. The name of the paper is this. And there is another paper by this Abramowski, this guy. That is called comonadic view of contextuality. So that actually the tools used in that paper is that category theoretical tool they have used in that paper. So you remember Somda was discussing something in this direction. So that paper was the first paper in this direction. But that used category theoretical language while deriving all these things. So I just avoided those things and just discussing a physical language, more physical language.
Very nice discussions. But yeah, so now I wanted to ask you these questions. For example, when Cabello is giving this 18 vector proof, okay, And so that actually gives some correlations, right? And actually that
Yes.
is state independent proof of non-contextuality, right?
Yes. Yes. Yes.
So if I take those 18 vectors and take any state, like if I take I by 2 also, I by 4 also, then I by 4 also can give me some correlations which would be non-contextual, which would be contextual,
Which should be contextual. Yes.
because that, since that is state independent proof.
Yes. 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 Sure.
Now what I'm asking, so if I take I by 4, what will be the contextual fraction? Or if I take any pure states, does that contextual fraction should increase for
Be-
that case?
no, because see, this contextual fraction depends on your data table, right? So
Yes.
what data table you are producing with your state and measurement, that will
Yes.
reflect in the value of the contextual fraction.
So that's why I'm asking. If you take I by 4, your data table would be something. If you take a pure states in C4, your data table would be something
That will be
else.
different. So the contextual fraction should be different for those two things.
Should be
Those
different.
two things are not equivalent.
So now what I'm asking, I mean, can I certainly say that a pure states, so suppose I give some measurements, okay? Some number of measurement is there, and I took some pure states, then the pure states would always give me higher contextual fraction than the mixed states. Can I make a comment like that? Or
Yes,
is there?
for mixed state, yes, for pure state, you will get some greater contextual fraction, as I can see.
But how are you so sure about it?
Because see, this Cabello's proof, this is only a logical proof, just shown
Yes.
some contradiction. Like there are two contexts where one value corresponding to one projector is different, no, for two different contexts. So that is just a logical proof. So it is not always possible to formulate an inequality from a logical proof. Is it always possible?
Can you repeat?
I mean, I'm saying that proof is like some proof by contradiction.
Yes.
Like some logical proof kind of thing. But
Yes.
while analyzing this contextual fraction, we first need such a data table. And that data table can come from the conjunction of your state and measurements. I mean, all the probabilities should reflect the state and measurements. So if you can produce such a table with some state which has maybe more non-classicality, then your contextual fraction will be more.
But I'm saying, I mean, how are you assuring that a pure state would give higher contextual value? How you are assuring this?
For the state independent thing, I mean, I have to calculate it. I mean, I mean, without calculating it, maybe I cannot say anything.
Good. Okay, because all the quantum mechanical state would, all the C4 quantum mechanical state would show violations. But then I was trying to understand, okay, what is the things? What is the main things? And okay, another things, for example, in Bell non-locality, shared LOSR, local operation, and shared randomness is not three operations.
Yes.
So and in this case, the free operation is so LOSR is a subclass for non-locality kind of things only, because in non-locality is a particular type of contextual scenario.
Yes, right.
And that's why LOSR would also be a particular type of free operations there, right?
Right.
So in your this free operation set, obviously LOSR would also be a free operations, right?
I mean, I think I have not calculated in my hand that, but it should come like from the giant free operation. If I restrict my scenario in non-local scenario only, then my LOSR should come back from this giant free operation. Only then this will be accepted.
Otherwise it would have some problem.
Yes. That is true.
Okay. Now another thing, just this is my last questions.
But that giant pre-operation is actually, you can see from the paper that giant pre-operation is very complicated pre-operation, but I have not tried it to reduce it to the LOSR kind of thing.
Obviously. Now let me ask you this thing. Suppose you take a C2 state, okay? And for the C2 state, can you give a few set of measurements for which finally it would be contextual?
For Kochen-Specker kind of contextuality, I cannot give, because for projectors there is a model already.
Exactly. So forget about the Kochen-Speckers. So you can, and when you are talking about, you are not talking about a projective measurement. You are actually talking about any kind of measurement, because you are talking with a probability, right?
No, but this I mean, when I
Oh,
was representing this
I
G,
see.
you observe that always I have written 0, 1, and outcome set was
Good.
0, 1
So this
only
is
when I
very,
first defined.
so this is, yes. So this is very specific kind of, this whole discussion is only for projective
Measurement
kind of
contextuality,
measurement.
yes, projective kind of things. Like
Okay.
it is comparable to Kochen-Specker kind of contextuality, but not
Good.
the Specken kind of contextuality.
Good. Now that's why let's go back to C3 systems only. And if I take a C3 systems, then again, okay, what is the minimal number of measurements for which I can come up to the contextuality?
I mean, the vectors are, I mean, 13 vectors proof are there. That is the minimum, I think. This U and
But
O.
that is a state dependent, right?
State dependent, yes.
Good enough.
Yes.
So now what I'm saying, so the 13 vectors proof is state dependent measurements, and then that gives it. Now what I'm saying, now you took a mixed states, then for the mixed states, the correlations, the behavior I will get, that would be non-contextual possibly, means for some mixed states. Now let's take, if I take I by 3, then I think for I by 3 it would be non-contextual. Okay.
Non-contextual, yes.
Now, if I take a mixture of this psi, which was giving me contextuality, and the I by 3, which was giving me non-contextuality, if I take their mixture, probabilistic mixture, then at some point the breakdown will happen.
Right.
Okay. So then I'm saying, if you suppose someone asks you to give an operational task with this Kochen-Specker contextuality, okay, then actually the state which is yeah, okay. So some of the state would be useful, some of the state would not.
Some of them will be not useful. So like for
with mixture of
C3, as you are saying, so for C3 we have a very good inequality, this KCBS inequality. For that you may, as you are saying, that some state will violate this KCBS, maybe some state is not violating the KCBS.
Good.
Yeah.
Okay,
good. Thank you.
Okay, thank you.
Okay, sorry. Shom, go first.
Thanks. I mean,
hello?
I just want to make a comment
Yes.
regarding that Cabello 18 vector proof. So the thing is that you define your contextual fraction in terms of strong contextuality, right? So, and the
strong contextuality and non-contextuality.
So strong contextuality, to define strong contextuality, you need something called support table. So where basically you make the non-zero, you have in the data table, you have non-zero probability and zero probability. So you make the non-zero probability 1 and zero probability will be remain 0. So that's called your support probability. Now, what Abramsky and Hardy showed is that, okay, in the earlier paper of the 2012 paper where they introduced these things, and one more paper where they showed is that, okay, if any particular probability table shows strong contextuality in the sense that, you know, it has the strongest form of contextuality reflected on the support, not on the data.
Yeah, okay. Understood.
So those things maximally violate the any logical Bell inequality you can construct.
Yes. So the model I written today, that pair box
Yeah.
model, that will violate the Bell inequality maximally up to 4.
Yes. So now, so in like we can define a contextual fraction in terms of support table for the support table also, right?
Yes,
Then
yes.
then any type of behavior that shows strong contextuality, like Kochen-Specker, like the Cavallo 18 vector thing, they all violate. They all have contextual, like maximum contextual fraction, right?
Yes, but Kochen-Specker, this Cavallo's 18 vector, it is not strongly contextual, right? It is just in between.
Okay, it is in between contextual. I forgot which type of contextual that was.
Yes. This Cavallo's kind of scenario, it is not strongly contextual.
Okay. Then it have some.
Actually, strongly contextual model or strongly non-contextual model, that are not realizable in nature.
Okay.
Because
Like it is proved.
No,
Because
I think because if someday you prove that quantum theory is not the governing theory of nature, then
ZZ
you
showed
can
a kind of
dispute this
strong
statement.
contextuality, no?
No, Cavalier proof used
Oh, you mean
the quantum theoretical prescription only, state vectors, right?
Okay. For the Cavallo's
So
proof. Okay.
yes, Cavalier proof. So that contains only contextuality, but not strongly contextual.
Okay. Thanks.
Yes.
Okay, Shumik. Now I have one question, last question, I guess,
Okay.
of this
Okay.
meeting. So it is also related to what Mir asked, and also you discussed a little bit. Like for any resource theory, it is a problem, no? Like how to determine the monotone and free operations. Like they are
Yes, right.
in a way both ways, or like where to start, right? So I would say that
I mean,
there
is some confliction, sir.
Yes. So there are debates. Of course, there will be debates. But
Yes.
one way is also to define some operational task, so which might be connected to this contextuality fraction. And I mean, then the problem is like for some information processing problem or something, first you show that non-contextual things are not useful. Okay. And all contextual things are useful. And then one tries to look at the either the success probability or something which is very like operationally realizable, and see whether it is connected to some quantity which is the monotone, which is the function of these behavior tables, or like the table you are talking about, right?
Yes. Then one can start with some point, like first defining monotone with respect to that particular task.
Operational task, yes. So I would ask, like for this particular thing, contextuality fraction, is there any operational task already proposed, or?
Yes. Some tasks are there, like some Boolean games. And also in quantum computation, there are some advantages that are achievable only when your contextual fraction is greater than 0. Something like that is there already.
Okay, so from that only, I guess what Mir was asking, that if you have any arbitrary state and if you play that game with only projective measurements and stuff like that, then you can get some contextuality fraction which is proportional to the success probability of the task, no?
Yes, exactly.
Okay. Yeah. Okay, and also, can you send the link for these operational tasks that are connected to this thing when you send the slide? Also, like because we want to share it.
I will send those link of those papers, like these 2-3 papers I was talking about.
Right. Okay.
And as well as share the slide also where you have written.
Yeah.
Okay. I'm sharing that slide also.
Okay.
Thank you, Sumit, for the nice talk.
Thank you. Yeah. Thank you everyone for joining. We are ending the meeting now. Mir, you can stop recording.
Wait, আমরা 3 জনই আছি